Welcome everyone to the USC AI Future Symposium. Our theme today is, will AIs ever be one of us? We are very excited to have more than 20 speakers and presenters sharing with you ideas about how to improve human-AI interaction. My name is Yolanda Gil. I'm the chair of this symposium. I am a researcher at the USC Information Sciences Institute and a research professor in computer science. And it is my pleasure this morning to introduce speakers that will give opening remarks. And our first speaker is Dr. Yannis Yortsos. He's the Dean of the USC School of Engineering. And he's also Zohrab Kaprielian Dean's Chair in Engineering and Chester Dolley Professor of Chemical and Petroleum Engineering. Yannis?
Thank you very much, Yolanda. It's a great pleasure that I am here, and the great pleasure that I welcome everyone to today's symposium. The symposium is focused on the research needed to make AI systems interact with people in the ways that we interact with one another. Hence the title of the symposium, Will AIs Ever Be One of Us? It's a provocative title, to be sure, but increasingly not so far-fetched. Can I dare extrapolate? Will AI ever be a dean of engineering? Today, we have AI systems that can converse about a dinner reservation, direct them to drive a car, or requesting a music. But it is very apparent that they do not communicate like we do. They know little about the world, ignorant of social conventions, cannot learn our quirks from numerous conversations, and seem clearly confounded when something unexpected happens. So AI needs more knowledge, which will be the theme of our first session. They need to learn to adapt to the user. That's the theme of our second session. They need to adapt to act and make decisions responsibly and ethically. That's the theme of our third session. And to be trusted with critical tasks that go beyond just entertainment or shopping, and that is the theme of our fourth session. This research agenda in AI-human collaboration has been put together by 20 plus USC AI faculty, and we will present an ambitious and interdisciplinary theme that connects very well with our own theme of what we call Engineering Plus, a theme that we have been advocating at USC for quite some time now. Essentially, one cannot design an AI system to just perform a target function. Rather, one should go beyond the function itself and also consider the user context in that design. And that requires partnerships with end perspectives from psychology, for example, human cognitive limitations, communications in the area of messaging, social sciences, when collaboration comes to the fore, ethics in the case of trust, and so many other disciplines. Today, many of our USC AI researchers are collaborating with other disciplines that look at the human side of that equation. For example, those at the USC Dornsife College of Letters, Arts and Science in psychology and social sciences. USC Annenberg School of Journalism and Communication, School of Social Work through the Center of AI for Society, the Price School of Policy, and so many other schools. AI at USC is a strategic priority. It's endorsed by our president, the new president, Carol Fold, and our new provost, Chip Zukowski. This very interdisciplinary environment at USC is suited ideally to develop it across all disciplines and all endeavors. And such synergies and expertise will be highlighted in this seminal symposium. Exploring the faults of the human-technology interface is an intriguing and extraordinary endeavor. I hope that you will find it exciting, stimulating, and inspiring. I'd like to thank Yolanda and many of other ISI and computer science colleagues for taking this initiative to organize this wonderful symposium on this important topic. So welcome again. Thank you, and fight on.
Thank you very much, Yannis. Our next opening remarks will come from Cyrus Shahabi. Cyrus is the chair of the USC Department of Computer Science, and he is the Helen and Emmett Jones Professor in Engineering and Professor of Computer Science, Electrical and Computer Engineering, and Spatial Sciences. Cyrus?
Good morning. Thank you, Yolanda. Thank you very much for inviting me to speak during this opening session. This is a very important symposium for us. As the Dean mentioned, AI is a priority for the school and specifically for our computer science department at USC. And as some of you know, we already have strengths in various areas of AI in the department, such as natural language processing, machine learning, robotics, and vision, just to name a few. And we are actively growing our faculty in these areas. For example, just this coming fall, 2021, we are onboarding 3 new tenure track assistant professors, and their areas is exactly NLP, robotics, and machine learning. And I'm saying at least because we are hopeful to hire a couple of more faculty during this hiring season. So this is a plug. If anyone is interested, we are hiring this semester, even though USC as a whole has a hiring freeze. One reason we can be so bold in growing is because of the new CS, computer science building that will hopefully be ready by fall 2023. Actually, I'm sitting right at the location of the building. This would be the view from the new building. And this new building is called Dr. Allen and Charlotte Ginsberg Human-Centered Computation Hall, or GCS for short. And as you see, there's an emphasis on human-centered, which means that we don't want to do technology just for the sake of technology. We do it for society and for people, whether this is AI for social good, for public health, like for helping with the pandemic situation, or as importantly, making sure that our algorithms are fair and ethical. So as the Dean said, if you want to have AI to be a Dean of Engineering, we need to make sure that the algorithm can be as fair and as ethical as Yannis, and actually that's a very tough goal. So I would like to end also by making one observation that our faculty members not only active in AI research, but they're also very active in leadership role in many AI organizations and conferences. I was just looking in 2020, and I see Yolanda, for example, as the president of AAAI. Sven Koeng, that I briefly saw his name, is serving as the chair of SIG AI in 2020. I think his term finished in 2020. Fei Shaw was the PC chair of AAAI 2020, and Yan Liu was the general chair of SIG KDD 2020. So again, I would like to thank the organizer for having me, and I'm looking forward to participating in this exciting symposium. Thank you.
Thank you very much, Cyrus. Our next opening remarks come from Craig Knoblock. He's Executive Director of the USC Information Sciences Institute, ISI, and he is Research Professor of Computer Science and Spatial Sciences. Craig?
Great, thank you, Yolanda. I want to welcome everyone. It's great to see so many participants in this symposium. That's quite an exciting event for us, and I'm hoping that you'll find it quite rewarding. So I just want to give a brief overview of what to expect today. So, well, the next 2 days. So, we're going to start with a session on harnessing information, which is going to cover things like controlling misinformation. Then we have several invited talks. First, we have Prem Natarajan from Amazon, who'll be talking about deep understanding. And then we have Antonio Damasio from USC talking about intelligence, brains, and humanity. Then we're going to have another technical session with a number of USC speakers talking about acting responsibly and ethically. And then in the afternoon, we have a panel session that's going to address AI agency, in particular legality, responsibility, and ethics. Then we continue tomorrow with a number of really exciting sessions. So we start out with a session on learning independently with a number of USC speakers. Then we're going to have a poster session. So I hope you'll all attend the poster session. You can interact with some of the faculty and students that have posters in that. Then we have another invited talk by Elizabeth Churchill from Google. And then a session in the afternoon on taking on critical tasks, a number of invited speakers on that. And then finally, we're going to conclude with another panel on human AI collaboration for navigating crises, which I think is a really important topic. You know, I think we have a really exciting lineup of speakers and events over the next 2 days. And I hope, you know, people will be able to participate in, you know, all or as much as you can in that. So I want to thank everyone for joining. And I think at this point now, we'll move on to the actual technical sessions. So welcome, everyone.
Thank you, Craig. Thank you very much. All right. Before we start our first session, which will start immediately, let me go over a couple of housekeeping notes. First, we are going to be recording the sessions and we'll need your consent when you push the continue button. The sessions will be posted publicly. You will be able to post questions in the QA window. So you will find it in your controls at the bottom of the screen in your Zoom. And the chair of the session will be looking out for the questions and will organize and figure out how to convey the questions to the speakers. All the questions will be at the end of the session. And the chair will be the one asking and organizing that question answer segment of the session. And without further ado, let me start the first session this morning, the first session of the symposium. The topic is harnessing information. And I want to introduce the chair for this session, Ralph Weischedel. Ralph is a long-time contributor of AI research, particularly natural language. He's a senior scientist and research team leader at USC ISI. And I want to give him the floor. Ralph?
Thank you. So our first of 5 presentations is Emilio Ferrara, Controlling Misinformation. Since these are all brief, I'm going to give very short introductions to everybody. Emilio.
Hello, good morning, everyone. Thanks for having me. It's a privilege to be opening this symposium. So today I'm going to talk about social media abuse and controlling misinformation. Next slide, please. So about 10 years ago or so, I became very interested in this idea on the possibility that a human would be mimicked, or a computer algorithm, if you like, could act and talk like a human on social platforms. This was the time when online platforms like Facebook, Twitter, and so on kind of arose to popularity. So they started attracting millions, hundreds of millions of users and so on. And I would argue that this question is sort of fundamental to computing. In fact, one of the founders of modern computing science, Alan Turing, posed a very similar question, you know, the sort of like the Turing test, if you like. Next slide, please. So I embarked onto this quest of understanding whether machines could disguise themselves online as humans. And there were a number of concerning applications where allegedly these so-called bots, which is a short for robots, were used. One example was, unfortunately, in the case of extreme radicalization and propaganda and recruitment efforts carried out by ISIS on online social platforms, where they reportedly used thousands of bots to engage with Westerners to recruit them. Bots were used to manipulate the stock market, to create buzz around companies, to inflate their stocks. And most importantly, if you like, bots were also used in the early 2010s to spread misinformation around natural disasters. For example, during the Hurricane Sandy in New York, many false news spread. And a lot of the work that we did during the 2015 and 16 was aimed at understanding the saliency of this problem and how widespread it was. And what we stumbled upon back then was a massive set of bots that were used, what turned out to be a Russian interference operation, 50,000 or more bots that were used to influence political discussion in online platforms before the 2016 election. This work also informed the Senate investigation in what turned out to be the Russian-linked Internet Research Agency operation. Most recently, what we've been doing is looking at the adoption of bots in modern day issues, looking at the use of bots to spread misinformation in the context of COVID-19 and in the recent 2020 elections. Next slide, please. So we looked at a large corpus of tweets that were collected by our group since the very beginning of the year, when we realized COVID might become sort of a pandemic. And as of today, we collected well over 1 billion tweets, starting again from January 21st. And we didn't use this data set only for our internal study. We thought it would be a very important resource for the research community. So we made it public in March, and there are well over 500 research groups that are using this data set as of today for research purposes to understand the chatter of, online. Next slide, please. We also use this to study misinformation and issues of social media abuse in Twitter regarding COVID-19. And unfortunately, what we found is that the very serious prevalence of bots that are used to spread narratives that are related to conspiracies, fake news, and so on. Now, if you look at the tag cloud or the word cloud in the bottom right corner of these, you will see what are the most common keywords and hashtags spread by bots in the context of this discussion. And you will see very popular hashtags, unfortunately these days, like QAnon and similar. And this is, there is a stark difference with respect to the topics that are covered by human users that are regard concerns in public health. But beyond bots, we also looked at what human users are discussing about, and we found that there is a sort of remarkable polarization that is driven by political divide. And bots and humans that are fighting about COVID-19 are also arguing and fighting about political dissent and insurgency and so on. Next slide, and then I'm gonna wrap up. In the 2020 election, we also ran a study that looked at conspiracies and misinformation. And in the next slide, I summarized some of the findings that we published very recently, just days before the election itself. Next slide, please. Where we highlighted the fact that bots have been sharing and diffusing and spreading misinformation generated by hyper-partisan websites like InfoWars, OAN, and Breitbart at higher rate, disproportionately higher than human users in specific states that unfortunately turned out to be very recently also driving some of the insurgency that we have seen on January 6th, taking the Capitol. And with that, I conclude my talk. Thank you.
Thank you. Since we're taking questions at the end, we're moving on to the next presentation by Craig Knoblock on threading data.
Okay, great. Welcome everyone again. So yes, I'm going to be talking about threading data today. So next slide, please. So the question of the symposium is, will AIs ever be one of us? And as Yannis mentioned early on, one of the key problems that we have for AI systems is acquiring information, right? They have to have enough knowledge about the world. And so as part of that, they must be able to understand these kinds of tables of data. So if we look at this table, if you look at this a moment, I'm willing to bet that most of you can actually figure out what this table is about, right? We're good at this kind of stuff, right? We have a lot of background knowledge. We can sort of look at this and sort of figure out what the table contains, what kind of data it is. Next slide. And so in fact, what this table is a table of drugs and the conditions that they treat, along with the names and the recent sales figures. And, there's a couple other things that's worth noting about this table. One is that, when you look at the numbers in the table, they're actually units that are represented in millions of US dollars. That's important to understand what the numbers mean. And also there's sort of a idiosyncrasy in the real table here, which is this sort of this extraneous space, but that doesn't seem to bother us at all, right? We would look at that and go, oh, that's, 19,936. Whereas a computer today might look at that and go, oh, there's two numbers there. One's 19, one's 936, but that wouldn't make sense to us. Okay, next slide. So why do we want all this data from these tables? Part of this work is part of the ISI Center on Knowledge Graphs, where we've been building knowledge graphs to address a number of societal types of problems. And some examples of the types of problems we're working on include fighting human trafficking, predicting cyber attacks, stopping penny stock fraud, and identifying threats in space. And in all of these areas, we built large knowledge graphs based on really huge amounts of data, a whole variety of data, including both text information, but as well as a lot of data from various kinds of structured tables. And the ability to pull in data from tables is really key to be able to building these kind of large knowledge graphs for solving these various problems. Next slide, please. So, okay, so I'm going to just address one of the three problems I mentioned a few slides back, which is, okay, how do we actually understand the content or semantics of a given table? So on the right is the table again, and as you see, there's actually a little graph above it, which represents what the table actually contains and how we represent sort of the interactions, the relationships across the different pieces of information, right? So this table is really about pharmaceutical products. They have some active ingredient, which is the main medication. They are used to treat some particular condition. There's a name for these, different products, which is the trade name. And then you have the different revenues for 2017 and 2018. So this is all sort of, information that you need to understand what's actually in this table. And, our idea, our goal here is to actually be able to look at these types of tables and build this kind of mapping or sort of description, the semantic description of what the table contains. And the idea is to do this is really to exploit the fact that there's a tremendous amount of existing knowledge out there in knowledge graphs, in very large knowledge graphs. In this case, we used DBpedia, sort of the key knowledge graph that contains a tremendous amount of structured data here, and we can use I'm sorry, not Wikidata rather. We can use the Wikidata ontology as sort of the underlying representation of the data. And we can also use the various sort of pre-trained machine learning models that are available to help understand some of the contents, right? To interpret things like the names, the column names that you see in this table, which helps us as humans actually understand what's in this table. Next slide. So let me quickly just walk through a few slides that give you a sense of the basic approach we use to solve this problem. So the first step is really we have to figure out what are the entities that are actually referenced in the table itself, right? So we have things in this table like under drug, we have the various drugs there, and then the conditions that they treat in the next column, and then the trade names. And it turns out that a lot of this data, or some of the data, is actually already in Wikidata. And even if we can only find a small percentage of that data in Wikidata, we can actually use that to help us understand what this table actually contains and what the relationships are. So for example, we look at this trade name Humira, we discover that in Wikidata, there's actually 3 different references to Humira, right? So there's a pharmaceutical product, a Czech company, and a journalist, all with that name. And we can sort of get this information using either something like Elasticsearch, where we can index all the data that's actually in Wikidata, or use similar things like embedding vectors, which actually help us find very similar names. Maybe they're not exactly the same, but very close. And so we can essentially, for each of these different references within the table itself, we can return a list of candidates and some sort of corresponding competencies, and use that to sort of tie the table into the actual existing knowledge graph. Next slide, please. Once we do that, we can essentially construct a graph of the relationships between these different entities and facts about the entities. And so we essentially do this by taking each of the entities sort of in the table itself and create nodes in this graph that we're going to create. And then we can, for each related node in the table, meaning if it's, for example, if two things are on the same row in the table, then there's probably some relationship between them. We can add a path from the actual knowledge graph. So we can look in Wikidata and look and see, well, what are the paths that get between those two entities within Wikidata, and really put that into the data graph as a possible relationship between them. And then we can also perform inference on this to essentially give you other things like transitive and symmetric properties from the graph. Next slide, please. Once we do that, then we have something that's, a graph of all the potential relationships that might explain this table. And what we want to do is go from this data graph to then infer a final semantic description, which we call the semantic graph. And so to do this, what we're going to do is we're going to add really you can think of each of the columns of data from the table as a node into this graph. And then you're going to add links between these nodes based on the links that are in the data graph. Then we can also use some pre-trained machine learning models to infer relationships between these columns based on the names and the headers. And then finally, we can take all of that information and use that to use what's called probabilistic soft logic, which is an inference system that we can use to then finally come up with what we think is the most likely explanation of what's in that actual table of data. And this probabilistic soft logic, we can use it to actually capture things like, okay, things that are in the same column actually belong to the same type. Okay, next slide. And then finally, so then we come back to the original question, well, are we there yet? And I would say no, certainly people are still much better at these kinds of tasks, but I'd say we're making progress. And I think one of the exciting opportunities is the fact that there's all this sort of recent both data and technologies that really make a lot of things possible that weren't easy to do before. So for example, we have these very large knowledge graphs like Wikidata, DBpedia, Wikipedia, and so on, that have a tremendous amount of background knowledge that we can exploit to help understanding what's in its very structured sources. There's all this work on learning these, these large pre-trained models like GPT-2 and GPT-3 that are very useful for understanding context and finding connections in the data. And then finally, there's these deep learning techniques that really are very effective at learning from lots and lots of existing data that we can exploit. And so, the ability to fully automate this type of table understanding, I would claim, is really going to revolutionize our ability to exploit the available data sources and bring us, a step closer to achieving this goal of actually having fully AI systems that are effective at interacting with people. So, thank you. Okay, back to you, Ralph.
Thank you. Needed to remember to unmute myself. All right, so our next presentation is by Wael Abdelmajid. Seeing is not believing. So Wael, please take over.
Thank you, Rolf, and good morning, everyone. And it's an honor and a pleasure and a privilege to be part of this panel. Next, please. So as Dean Yannis mentioned in the morning, AI systems are great for simple things like recommending music and movies on Netflix, etc., etc. However, there are some fundamental aspects of machine learning that are, as Dean Yannis mentioned, completely ignorant to some social norms and other constraints that basically require us to have a deeper look into how these AI systems work. And I would like to start by sharing two stories, and then we will dive deep into what I mean by seeing is not believing. So this is a story about Jennifer, and Jennifer is a 9-year-old girl in Miami, Florida, and Jennifer and Sarah basically started getting to know each other through one of a million different social networks now that are extremely even difficult to count anymore. Sarah is about 11 years old, and she tells Jennifer that she just recently moved to to Miami with Beth, her mom, Matt and Noah, her brothers, and Scott, her attorney, and they just moved from somewhere in Ohio. And Sarah actually wanted to get to know Jennifer more and wanted to know her schedule in terms of having play dates and knowing where Jennifer is going to the park, so Sarah can join and they can have a play date together. It turns out, can you click next, please? It turns out that Sarah is actually not real, and this is Mr. Hyde, and Mr. Hyde wanted to know Jennifer's schedule so that he basically can assault her in the park. So I'll let this story marinate for a moment in your head while you watch this video as well. Yolanda, there is no audio. So since there is no audio, basically this is a video of President Nixon basically saying that the men who went to the moon will forever stay on the moon, and the Apollo 13 mission completely failed, and the astronauts will actually die on the moon. This video came about 4 months ago, came out about 4 months ago, and this is one of the new classes of videos that basically are called multimedia, deep fakes.
Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace.
Thank you. So obviously, as you all know, this is not true because this mission has been over 40-something years now, and the mission actually was a success. And the astronauts who went to the moon came back to Earth. And again, this is a new family of videos that are called deep fakes. They are fakes because they are not real, and they are deep because they have been generated by a deep neural network. Next, please. Well, the good news is that I let the story of Jennifer marinate in your head for a while. The good news is that I basically invented that story. That story never happened. But the reason I mentioned that story is that every single character in that story, from Sarah to Jennifer, even Mr. Hyde, I basically created these characters using AI. These people do not even exist in real life. All of the images that you have seen here are AI generated. And of course, the Nixon's video is also AI generated. Next, please. So in the last 5 years, we have been investing heavily, my group and I have been investing heavily in developing AI algorithms that actually can figure out if a given piece of media is fake or real. And as you see here on the right-hand side, these are some examples of recent work that we have been doing. We developed multiple generations of neural networks and AI systems that can look into an image and say that this image is actually manipulated or photoshopped or doctored or however you want to call it. And we also can pinpoint where the manipulation is. And if you can play the video on the left-hand side, please. It's a shorter version of the same video.
Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace.
So as you can see here, this is the output of processing the same video using our second generation of deepfake detectors. On top of each frame, we overlay an indicator that basically shows that this particular frame is AI generated or real. And on top of the video, you see a sort of a progress bar indicating which parts of the video are real or fake. Next, please. So what's multimedia forensics? Multimedia forensics basically is any research using AI algorithms or machine learning algorithms that can ensure the integrity of digital, whether it is digital, semantic, or physical integrity of a particular multimedia asset. It also ensures the authenticity, origin, and provenance of that particular multimedia asset. Where did it actually come from? However, we have to do that without actively embedding any security, such as watermarks into the multimedia asset. So basically, we look into any multimedia asset and decide whether it is fake or real. Why is that important? As you have seen, it ranges from child safety to criminal justice to international propaganda and national security. And as Dean Yannis mentioned, this is basically the interaction with society aspect of these AI-generated multimedia, because they can actually increase. They have been increasingly been used for polarization and spreading conspiracy theories. Next, please. That does not mean that AI researchers are not completely innocent of this, because we cannot just, at least from my perspective, we cannot just create very dangerous AI algorithms without thinking about the social interaction between these AI agents and the world. We cannot just say we will take the credit, but other people have to decide whether this is a serious problem or not. Next, please. So I'm one of the advocates who basically think that the AI community needs an internal debate about the ethics of using AI systems and what AI systems we as a community need to develop. Before we get regulated by the government and lawmakers, we need to start thinking about self-censorship. Every AI researcher should start asking questions like, what could an adversary use my algorithm for? Should I release the code or not? I understand that security by obscurity is not a good idea, but it's just one more barrier. Basically, we need to start thinking about what research should I do or should I not do, because I have moral and ethical constraints. Next, please. And finally, this is some of the media coverage for the work that my group and I have received lately, including Forbes, Times, Fox News, and some French coverage as well. Thank you. I'm looking forward to your questions.
Great, thank you, Wael. Let me point out that a couple of you have used the Q&A. If you're not familiar with that, there should be an icon at the bottom of your screen. It's in the center of my screen at the bottom. Click on that Q&A icon, and you can enter your questions there. I'm monitoring that so that we can answer them at the end of all the presentations. So our next presenter is Ram Navatia on multi-source synthesis. Ram, thank you.
Thanks, Ralph. Good morning, everyone. Our theme is, will AIs ever be one of us? Obviously, there are many, many requirements. I'll focus on one. Clearly, machines should communicate with us in natural language. Most of us don't like to talk in Python. They also must be able to perceive and interact with the real physical world. And these two things should come together. The real world should be described in language. If there's a query in language, we should be able to find the corresponding entities in the real world. More formally speaking, we could say there's a storytelling ability to describe what's going on, as well as a query ability to understand the commands or communications that might be provided by a human. I will focus on just one aspect, so-called grounding. Next slide, please. So, of course, we all construct object detectors by name, machines that can find cars, dogs, cats, and so on. But there really is no meaning to those names. They could just be IDs, category 1, 2, 3, and so on. When we go to phrases, that luxury is no longer there. So if we want to find person in white shirt riding a horse, an animal on the right, head of the person wearing blue shirt, we can't possibly take each such phrase, gather training data for them and treat them as if they were just a category, because there's virtually infinite number of such combinations, unlimited number of such combinations. So the approach to this is a grounding pipeline. It's very similar to traditional object detection. In the image, we find boxes, so-called proposal bounding boxes that might contain some object. Look at the features of that object and decide what that object is. But if we are trying to ground a phrase, then in the blue box below you will see that the query phrase is converted to its own feature vector. Then we concatenate the feature vectors of the vision coming from the vision and from the language, and use the combined feature vector to see if the two go together through a classification pipeline. Next slide, please. So an almost essential requirement is that we be able to deal with novel compositions. For example, on the left, in the training set, we have a red car and a blue shirt, but at the test time, we have a blue car. We have not seen blue car in training before. Can we recognize this kind of an object? The pipeline I very briefly described will function if the following hypothesis is correct, that the language and vision features in the multimodal space define a smooth manifold. Basically, blue car requires us to do some kind of interpolation in this multidimensional space, and the manifold needs to be smooth or we won't get good answers. Next slide. We wanted to extend this notion of novelty to include categories that are not seen, not just the combinations of adjectives and nouns that are not seen. Let's say that truck, chair, moped are objects that we have not seen. Though we may have seen similar objects like cars, sofas, bicycles. So can we find red truck, blue chair, moped, even though we have not seen, our system has not seen truck, chair, mopeds before? There are some assumptions required to be able to do this, either by an AI system or even by us as humans, that similar language embeddings have similar visual features. So if truck and car are considered similar in language, do they also have visual features that are similar? The other difficulty is that the proposal generation itself may be deficient. We may not even get a hypothesis around the blue chair because chair was not part of the training set. Next slide, please. So we construct a proposal-free pipeline. Essentially, it creates proposals at every place on a grid at multiple scales. So the pipeline is somewhat similar to what I described before. There is a language feature embedding, there's visual feature embedding. They're combined into multimodal features at multiple scales. They go to a classifier. In our terminology, we would call it a single stage pipeline, and it is trained with an annotated grounding data set. The work is from a paper published in ICCV 2019. Yes, next slide, please. I will not have time to describe in full detail, but there's a lot of ambiguity in what can be called zero-shot cases. For example, there may be a new word, an automobile, but the system is already trained on a car, so it's just a synonym. Or the object category itself may not be seen. For example, not only is the chair not seen, but the system doesn't know about furniture category. the counter of it is the system does know about other objects in the same supercategory, but does the image contain both types of entities or not? Let's say the system knows about cars and there's a truck that it doesn't know about. If a car and truck are both present, the system may be more confused and prefer to call the truck as a car because it's familiar with cars. Next slide, please. So here's some visualized examples. The red box is the ground truth and the green box is the prediction. All of these are zero-shot examples. So cigar on the left, couch, countertop was found incorrectly. The green box actually includes the whole kitchen, not just the countertop. Next slide, please. 3 more examples, some of them quite difficult. The rocky cliff, shorts on a person, and a planter example. Of course, visualized examples, we can cherry pick good examples. We can show you one bad example. We'll also have quantitative analysis, which I'm not presenting for lack of time. Next slide. So we'll just summarize that I've introduced just one language plus vision task, which is that of grounding objects in images using noun phrases. If we go to videos and actions, we have a much richer domain because there are activities, there are objects, there are relations. We need to be able to talk about semantic roles played by the objects in the action. Counterpart to what I've described is caption and story generation from images and videos. Somewhat same kinds of technologies are needed with some variation. Visual questioning answer is we're given an image or a video and a user asks some queries about what happened, how many entities were present, and so on. An interesting side remark here is that there are many such data sets and you get better results by not looking at the image than by looking at the image, even though you're answering questions about the image. So there are strong biases in data sets that must be considered. So we have a whole bunch of exciting problems. We're just at the beginning stages. There's only 2, 3, 4 years of work in trying to relate language and vision. So we have a long ways to go and going to have an exciting journey. Thanks for your attention.
Thank you, Ram. So our final speaker in this session is Elizabeth Boucher on Providence Matters.
Hi, everyone. Okay, so I'm the last one in the lineup here. So I'm going to try and talk a little bit about provenance. So keeping track of the origins of our information, where it comes from, and why that matters. So I'm going to start with a true story. I was making cinnamon rolls over the break, and I asked Google how much a half cup of cream cheese weighed. And it showed me this table, which in retrospect, I think is actually wrong, but it didn't show me where the table came from, and I wasn't quite sure. I ended up having to walk over to my office and look it up on a real computer. And anyway, these are the kinds of things we deal with every day, and it's made much worse when we're dealing with large volumes of data or when we're a machine trying to draw conclusions from a lot of different sources. So I think there are 2 primary dimensions of provenance that we care about. I'm going to talk a little bit about them. So on the one side, we care about whether a piece of information, as written or as spoken, is true. So we can debate the nature of truth politically and philosophically, but let's leave that aside for just a minute. We do care about who it was who reported the number of people at a rally. And we care about when they reported it. Did they report it in the heat of the moment, or did they report it the next day when maybe they had more complete information? We care about whether they are being sarcastic or whether they're being serious. There's all these different elements there. And that's one dimension. But there's a second dimension we care about as well, which is the machine. So the machine that's trying to harness all of this information. Did it do its job right? So the document says the rally took place in Georgia. And let's say that's true. Right? Objectively, that's true. That's where it took place. In the first dimension, that's true. But the machine could easily read it wrong. It could think it took place in Georgia, the country, rather than Georgia, the state. And that's it's really important to keep track of that. And it's also really important because people tend to conflate these two dimensions and only talk about one or the other. And I think one of the things we need to do is make sure that we simultaneously pay attention to them without muddling them together. So I'm going to try and break them down just a little bit. So the first is truth, right? And I wanted to emphasize that this isn't just about fake news or deliberate misinformation, right? That's a really interesting topic, as we've heard, but that's not the whole problem, right? So next slide. There are a number of other dimensions we need to care about as well. So real news is always still biased, whether by a political slant or a geographical slant. It could be what is stereotypically called bias, like one source calls this guy a communist and one source calls him a centrist. Or it could be about coverage. So if you read one news source, you might hear that my hometown of Boston is a cesspool of crime. And then if you read another news source, it might seem like some sort of blissful utopia of peace and togetherness. And both sources might actually be running stories themselves that are actually true, but of course they're carefully selected, and that matters too, right? Time frame also matters. One of the things we've tried to harness information to do is to be able to predict the future, right? And the idea being, so one of the projects that I've worked on, if you can pull out all of the events that are happening in the current news, you can project them into the future and say, okay, well, I predict in 6 months there's going to be a coup in Thailand. But if you're going to do that, it really matters. Are you looking at data over decades, or are you looking at data over months? Right? And then finally, I would say another really significant problem here that AI has to address as we think about provenance is nested provenance. So here I have a sentence. The state security services claim that everybody it kills is a member of Boko Haram, and Boko Haram claims that everyone they kill deserves to die, said former US Ambassador to Nigeria, John Campbell. So the news agency says that the ambassador says that Boko Haram says something. Right? This is complicated to represent, and it can computationally explode right in front of you, and it can be a real problem. Okay, so these are all aspects of truth. Then there's the second question of, did the machine read it right? So reading is hard. Even humans get it wrong sometimes. So this is an example I use a lot. If you just have this sentence out of context, Daryl talked to Jack about his problems for an hour. Whose problems are they? You need context to understand that. You need to understand that if Jack is a therapist, then they're probably Daryl's problems. Or if Jack is an oversharer, then they're probably Jack's. And these are the kinds of decisions machines are trying to make when they interpret human language. And sometimes they get it wrong. Even the fancy new models that we've seen in the last year or two, sometimes they get it wrong. So the question is, well, do they at least know when they might be getting it wrong? And the answer is, of course, sometimes, right? And there's about 1 million different techniques we use to estimate this, right, in our field. And so you can look at decision boundaries. You know, if the machine says, well, I almost picked this one instead of this one, well, then it's probably not that confident in this one, right? You can look at voting a bunch of systems. You can build a bunch of systems, ideally as differently as possible. And if they all agree, then maybe they're all more likely to be right. So we just did this recently with 3 systems that were extracting events from news. And each of them was about 60% accurate, give or take, in terms of when it found an event, how likely was it that it was correct. But if 2 of the systems found something, suddenly it was 95% of the time they were correct. And if all 3 found them, it was like lights out. It was like more than 99%. So we know this kind of thing works as well. We can pull it off. And we can estimate confidence on held out data, saying, well, last week on this data set, when I tried to resolve pronouns, I got them wrong 30% of the time. So I'm only going to give myself a 70% confidence. And there's a ton of other ways that we can do this. So why does this matter? If you can't say why the machine believes something, people won't trust it. That's probably too strong a statement. People trust a lot of things, but there's a lot of important people who won't trust it, right? And that does matter. And it matters as we try to make big decisions, not just how much cream cheese to put in the frosting for my cinnamon rolls, but big decisions about, you know, what are we going to do about this or that political problem? And so here's just an anecdote to close this talk. So a few years ago, we were building a new event coder, right? So this kind of system that reads the news and finds the events and feeds them to models that predict political unrest. And we made an event coder that was way better than the one it was before, like twice as good. But the accuracy of the political forecasts didn't actually change because it turns out that those forecasting models were actually pretty good at dealing with the kind of systematic noise that was coming out of the previous event coder. But the problem was when the underlying data was that noisy and unbelievable, when you had someone who was trying to use the system and say, well, you told me there's going to be a coup in Thailand and you want me to do something about it, why should I believe you? And then they would look back at the data and they couldn't trace back to anything reliable, right? And it made the system not particularly usable, right? So then once the underlying data became much more reliable, they were actually able to show it to human beings who were looking at the data who said, okay, actually this system is useful. I believe what you're telling me, at least I understand why you're going to do it. And the users were more willing to adopt technology as a result. And this is part of the larger push towards explainable AI. And so basically the bottom line of my talk is just provenance matters, right? You need to represent it, you need to reason over it. And if you actually do that, and if you deal with all the challenges involved, you'll end up with richer and more useful and usable information as a result. Thanks.
Thank you, Liz, and thanks to all of our speakers. We do have some questions. The first one is directed to Craig. The slide on the semantics of a table is the best visualization seen. I have a lot of difficulty explaining this to upper management. Will a copy of the slides be available?
I believe we're planning to make both the slides and the videos from the whole session available on our website after the event. So it'll be posted on the page where you went and got the information about the symposium itself.
Great, thank you. Then a second one for you. How can human experts help with threading information?
That's a really good question. So in fact, I think that's a really important issue because it turns out that we're still a long way away from being able to take a table like the one I showed and have the system completely automatically understand what's in that table and how to represent it. And so I think having systems where the human experts can work with the machines are going to be critical, right? So that you can try to automate a lot of these kinds of tasks. And then you're going to need a person sort of involved in the process. And one of the challenges is how do you build sort of user interfaces and systems that humans can actually interact with and sort of exploit the information that the system can do automatically, but still make corrections or guide it down the right path. And we've done this in some of our previous work. So we have a system called Karma that is also used for modeling data. And one of the things that made Karma very successful was the fact that we really thought hard about the user interface side of it and how the human or people would actually interact with the system and allow the human to actually guide the system in terms of building the models that you have. So I think for a while still, we're going to need systems that very much support that kind of capability.
Great, thank you. All right, a question for Weischedel. What's your take on the current trend of not sharing models due to privacy or ethics concerns? For example, GPT-3 and OpenAI.
So I have a couple of things to say about this. I am not really with or against sharing models. What really matters to me is that, and this is pretty much sort of an agreed upon sentiment in the whole AI community now. Models and data live together. We cannot just share a model without data in a vacuum of the training, the data that was used to train this model, and just say for the whole community or somebody, go ahead and use it. That doesn't give any credibility to that model for me, because everybody knows now that models are biased and models can be reverse engineered, et cetera, and there is a lot of problems. If somebody wants to share a model, at least you need to share the data. AI models and data live together. That being said, there are different issues with different types of data modalities. For example, racial bias in terms of face recognition systems can be reasonably mitigated if we carefully select the data with which we train the model. If we select a racially balanced data set, the model is likely to be racially less biased. Language is a different issue in terms of GPT-3. Language has a much bigger problem than vision because racial and gender biases are built into our language for thousands of years. So that's a different discussion, but I just want to differentiate between different types of biases in data. Again, but as I said earlier, if somebody wants to release a model, you need to release the data set that was used to train the model. Otherwise, at least to me, the model doesn't mean much.
Thank you. All right, a couple of questions for Liz. How do you decide which provenance you keep or you throw away, given that the volume can explode?
Yeah, and the second question is essentially the same. I bet you're both typing it at the same time, right? And so I actually had a slide on this in my presentation and I took it out because I decided it was a whole other presentation. The title of the slide was something like, if you try to please everyone, you'll end up pleasing no one. You have to think about the downstream use case, right? You cannot store every possible piece of provenance that you want to for every possible thing. And so you have to think about, how are we actually going to use this data at the end of the day, right? And so, for instance, I have one customer dealing with data who really predominantly cares about, well, just is this pro-Russian or is it not pro-Russian, right? So if you can reduce it to a couple of different dimensions, then you can store that and move on. Now, obviously, that's not always a luxury that you have. You don't always have the luxury of knowing how your data is going to be used down the road, in which case, the only advice I have is try to come up with some sort of minimal, clean set of data that you can store. Like, oh, well, this is at least the high level data source that it came from, the New York Times, right? Or Twitter, or this segment of Twitter. But really it has to vary by use case. And you have to think about how it's going to be used at the end of the day, because you don't want to keep around a whole bunch of stuff that at the end of the day, you're just going to throw away.
Great, thank you.
I'm sorry, I'm mindful of the time. Do you want to ask one last question and conclude?
Sure, let me ask one for Emilio. What issues do you plan to study next?
So I think that at this point it's clear that the models that we are developing to detect these forms of abuse of online platforms work fairly well when we are looking at specific data modalities, for example, text. When we look at specific cultures, for example, American or European cultures, when we look at specific languages, most prominently English and so on. But it's still very hard to determine whether these models can be generalized to other languages, to other cultures, and so on. So a lot of work in progress is attempting to generalize these techniques to, different things, looking beyond false news, misinformation, bots, conspiracies, and so on. There are a lot of other forms of problematic behavior and misbehavior online that occur all over the world. So that's the frontier.
Thank you very much. Thank you, Ralph, and thank you to all the speakers for this really great session. We are going to take a break and we will resume at the top of the hour with an invited talk and look forward to seeing you there.